So in the previous module, we were talking about linear variation treatment, and we applied the linear variation treatment to a problem of particle in a one-dimensional box, and we saw that what kind of energy eigenvalue we get. Okay, and in the basic premise of the linear variation treatment is that you have to guess a trial function psi trial, and that psi trial is actually a summation of different function phi I with a coefficient Ci, which is the variation parameter for I to n, whatever is the number of particle or number of functions you can take. Okay, so this psi trial function we take in the linear variation treatment, and since it's a linear combination of different functions, so it's called linear variation treatment. Okay, and what we did last time, if I remember correctly, what we did was that we took a function x into a minus x plus x square into a minus x square as the function of psi trial function for the particle in a one-dimensional box, and we calculated the eigenvalue corresponding to this trial function, and we found that this trial function gives you an energy which is very close to the ground state energy which we obtain from by applying Schrodinger wave equation to particle in a one-dimensional box. Okay, so this was the things which we did in the previous module, and now with this in this module I am going to apply the linear variation treatment to another system called H2 plus molecule ion. H2 plus molecule ion is again, it's a 3-particle system. Okay, so it means you have 2 nucleus and 1 electron. So we did this earlier also. If we write the equation for potential energy, then this equation will have, if it is a hydrogen atom, then nucleus will also have the same charge, and if we say unit charge is there, which is E, then we have a potential energy term minus E square by R, which is the attractive term, or R1 I would say. Then you have minus E square by R2, and then you have plus E square by R. So plus E square by R means plus sign will indicate a repulsive term. So this is your potential energy term. If you start writing the Hamiltonian, then what you need to write? You need to write minus h cross square divided by 2m. Then you have a 3-particle system. So say I would say del 1 square minus h cross square divided by 2m del 2 square, and then minus h cross square divided by 2m del E square. Okay, so this is your kinetic energy term, and then plus this potential energy term will be minus E square by R1 minus E square by R2 plus E square by R. Okay, so the potential energy, the Hamiltonian is actually, in general, the Hamiltonian is minus h cross square divided by 2m del square plus V. Okay, this is what we say. So this is the kinetic energy term, first term minus h cross square divided by 2m del square, and plus V is the potential energy term. So potential energy term will have 3 different terms, 2 for the attractive interaction, 1 for the repulsive interaction. But kinetic energy term will have 3 different terms for each for 1 particle, 2 nucleus, 1 and 2, and E for the electron. But what we say is that Born-Oppenheimer's approximation gives you a leverage that you can neglect the consider the nucleus to be a static, and then you can neglect these terms of nuclear kinetic energy, because you suppose it to be frozen or static, and the electron is moving in the field of the nuclear charges. So we can, this approximation leads to only one term, that's for the electron, minus h cross square divided by 2m, h cross square divided by 2m del E square, and then rest of the term is this one. Okay, so if you apply the, again you see the Hamiltonian is complex because of the potential energy term, and we cannot have a solution for this system. H2 plus molecule ion is a problem which you can deal with in molecular orbital only. Valence bond theory In valence bond theory, we don't have a concept of forming H2 plus molecule ion, but anyway, molecular orbital theory does have a concept, and what we say is that two nucleus of hydrogen atom and one electron is there, that I said you. Each atom is represented by orthonormal wave functions psi A and psi B. The H2 plus molecule ion wave function must have a contribution from both psi A and psi B. Both psi A and psi B are the wave function for hydrogen atom, so they have the same symmetry, same energy, and capable of overlapping. Now, there is a principle called linear combination of atomic orbital, with which I think we came across earlier also, which says that if you have a similar energy, if you have the similar symmetry, and if you have the same orbitals which is capable of overlapping, then you can combine them to get a wave function which then you can linearly combine them for a molecule. So we can combine psi A and psi B because both are the wave function for the hydrogen atom. Both nucleus is hydrogen nucleus. Okay, so you can combine psi A and psi B and get a psi MO, which is the trial function. Trial function now we will say psi MO in the molecular orbital theory. So psi MO will be Ca psi A plus Cb psi B. Okay, and if you look at this equation, we already did this, and I said you that when you take a trial function of two wave functions, you get a 2/2 determinant, and that determinant was, if you remember, was HAA minus ESAA, HAB minus ESAB, HBA minus ESBA, and HBB minus ESBB, where HAA and HBB, I said you it's what? Which integral we say? These are Coulomb integral. These are Coulomb integral. Then HAB is called exchange integral or resonance integral. Just a recap of what you have already done. Exchange integral or resonance integral. Okay. Now SAB is called overlap integral. And SA and SBB are actually the normalization terms, where you have psi A deta or psi B deta, so that will be equal to 1. Okay. So this we did when we talked about the LCAO and secular determinant. So these integrals is already, you are aware of these integrals. We will talk about in details also. Okay. Now, since it is a hydrogen at H2 plus molecule ion, so both the nucleus which is combining is hydrogen nucleus, or hydrogen atoms are combining, and two hydrogen atoms, when we combine, one electron is removed. So you get H2 plus molecule ion. So what does it mean? The wave function which you are combining is the same wave function hydrogen atom, and in the hydrogen atom electron is in which orbital? 1s orbital. So 1s orbital, you have seen what is the value of psi 100 in the solution of hydrogen atom, or in the solution of hydrogen atom, you have seen what is the psi 10, a constant multiplied by exponential minus r divided by a naught. Okay, we will talk about this later on, but anyway, just so your psi A and psi B both are equal, and if you write the integral HAA, what do you write? HAA integral is psi A, then Hamiltonian I have written psi A deta. If you write psi HBB, then it is psi B H psi B deta, HAB psi A H psi B deta. Okay. So what you see here, this psi A and this psi A is the hydrogen atom. This psi B is the hydrogen atom. This psi A and this psi B is the hydrogen atom. So what does it mean? HAA and HBB are equal because both psi A and psi B are same. So if you look at this one, both psi A and psi B belong to hydrogen atom. So HAA will be equal to HAB, HAB will be equal to HBA. Okay, the same thing, because if you write HBA, what will you write? You will write psi B H and psi A D2. And since psi A is equal to psi B, so what does it mean? HAB and HBA is same thing. So HAB and HBA is same. Same way, SA and SBB will also be same, because SA you write as psi A D2, and SBB you write as psi B D2, and SAB we will write as psi A B D2. Okay. So there is a correction here. Psi A, psi B, this should be S. This should be S. Make the correction here. SAB is equal to SBA. So obviously SBA if you write. So SBA is what? Psi B, psi A D2. So SAB is equal to SBA. Means this is all because psi A and psi B are equal and both are eigenfunction of hydrogen atom. Okay. If that is so, then what you can write? You can write this as HAA minus ESA. This term you can write as HAA minus ESA. This term you can replace. And then what will be the value of the determinant? It will be HAA minus ESA square, and then same way HAB and HBA you can replace. So HAB minus ESAB square. That I can write very easily. Okay. Because both the contributing atoms are same hydrogen atom. Both the contributing atoms are same hydrogen atom. So we can write it like this one. Now what you say is that for positive roots, if this is square, so you can equate it and you can get this value. Okay. For positive root, what you can write? HA minus ESA, HAB minus ESAB. And if you rearrange them, what you get? You get HA minus HAB divided by SA minus SAB. Equation number 1. So one of the energy value for the positive root which you get is HA minus HAB and SA minus SAB. Same way, for the negative root, you will get another energy. For the negative root or lower energy, you will get HA minus ESA and minus HAB plus ESAB. You see, you look at this one. This is what you get, HAB minus ESAB. So what you get is minus HAB plus ESAB. And finally for E plus, what you get is HAA plus HAB, SA minus plus SAB. So two energy values we get. One is for the positive root, another is for the negative root. We get two energy values. Okay, out of the two roots, upper root equation 1 is upper energy level and lower root equation 2 is the lower energy level. So two different energy levels we obtain for the H2 plus molecule ion, which is made up of two different hydrogen atoms. We will see why I am writing it like this one. Okay, so this was your hydrogen atom. This was your hydrogen atom. This is your H2 plus molecule ion. Okay. Now, this if we have this energy value, HA minus HAB divided by SA minus SAB and HA plus HAB divided by SA plus SAB, and you say that two different energy levels are there, then there must be an energy gap between the two. So let us calculate what is the energy difference between these two energy levels. So if you calculate delta E value, even before that, we want to find out in the original equation where I have written here is Ca and Cb is the coefficients of psi A and psi B, which tells you that how much is the contribution of psi A function and how much is the contribution of psi B functions. So let's first find what is the contribution of psi A and psi B to the H2 plus molecular and molecular orbital. So if this was the two equations we can write, so two simultaneous equations which you can write from the determinant is like this one, Ca Ha minus Esa Cb Hab, because your determinant was Ha minus Esa Hab minus Esab Hba minus Esba HBB minus ESBB. Okay. So this determinant, if you remember, in the variation theorem, we got two equations with the two unknowns. Okay. So we have written the determinant. Now again, I am writing from the determinant the two equations. So you have psi A coefficients here and psi B coefficients here from the first row, and from the second row you write HAB minus ESAB, HBB minus ESAB, this coefficient. Okay. If you put the values of the energy which we have obtained in this equation, then what we get? If you look at the first equation, if we write this first equation, then Ca Ha remains same, then Sa is same, and this is the energy value, Ha plus Hab, Sa plus Sab. Again you write Cb Hab, then minus Sab, Ha plus Hab, Sa plus Sab is equal to 0. And if you solve this one, what do you get? Ca, then this you can write as HaSa plus HaSab. One of the steps I have not written knowingly, that you can write it and then expand it. So you have HaSab minus HaSa minus Sa Hab. Then Cb will be Hab Sa, Hab Sab, then Sab Ha, Sab HBB. So look at this one. This will go Sab Hab Sab Hab. This will go. This will go. Okay. So the equation which you get is Ca is equal to Ha Sab minus Sa Hab. Cb is equal to Hab Sa minus Sb Ha is equal to 0. So 4 terms will go and rest of the 4 terms will be there. Okay. If you rearrange this, then what do you get? You get HaSab minus HabSa. So what we did? Ca terms, HaSab minus HabSa, it's the same term. Cb Hab, it's a minus sign is given, so this will come here, Hab minus Sa, and this will come here, Ha into Sab. Okay. So what you can write? HaSab and HaSab, Hab Sa, Hab Sa. So this term and this term is equal. Okay. So this you can take common, and then you have Ca minus Cb. Okay. So a common term is this one, and Ca minus Cb is equal to 0. And for this equation to be valid, Ca minus Cb should be equal to 0. And if that is so, then Ca is equal to Cb. It's very simple. So what does it tell you? It tells you that contribution of both the eigenfunction A and B is same. Okay. Contribution of both the eigenfunction is same, equal. Okay. We have used the value of energy, which is Ha plus Hab, Sa plus Sab. But another value of energy is also there, which is Ha minus Hab and Sa minus Sab. So if you put this energy value, Ha minus Hab and Sa minus Sab, then what you will get? You can do it. Just practice it, and if you do it, you will get Ca plus Cb is equal to 0 instead of Ca minus Cb is equal to 0. And if Ca plus Cb is equal to 0 means Ca is equal to minus Cb. So if you look at these two equations, Ca is equal to minus Cb and Ca is equal to Cb, then what you can write is Ca is equal to plus minus Cb. Okay. So if you take Ca 1, then Cb could be plus 1 also and minus 1 also. And now if it is so, therefore Ca is equal to 1, then Cb is equal to plus minus 1. And what was your psi mo? If you remember, psi mo was Ca psi A plus Cb psi B. So out of these two, if you take Ca is equal to 1 and Cb psi A, so if you take Ca is equal to 1, then Cb could be plus 1, so Ca plus Cb you can write. And here if you take for plus 1 value of Cb and for minus 1 value of Cb, what do you get? Psi A minus psi B. Okay. So two different wave functions, eigenfunctions we generate, psi A plus psi B and psi A minus Cb. We have not yet normalized the function, we will normalize it. But just look at these two functions, psi A plus psi B and psi A minus psi B. If you have the hydrogen atom wave function psi A, and if you square this psi A square and multiply it by a volume element and then integrate it, what do you get? What you get is probability. Okay. If it is normal, then it is equal to 1, otherwise it will give you probability. What will happen if you have wave function psi A plus psi B? Okay. And if you want the probability P, then how do you find out? Psi A plus psi B square d2. Okay. If you have psi B as a function, then how do you find out the probability? Psi B square d2 will be the probability. So you do a square of this one, you do a square of this one, and you get the probability. Sorry, a square I already did it. Okay. Probability, I would say probability instead of this. So individual functions psi A and psi B gives you probability of finding electron as psi A square and psi B square, summation of psi A and psi B. Okay. So if you add these two probability, what do you get? You get psi A square plus psi B square. But if you have a after linear combination of atomic orbitals, the eigenfunction which you have obtained is psi A plus psi B, and if you square this one, what do you get? You get psi A square plus psi B square plus 2 psi A psi B. So what does it mean? It means that two independent hydrogen atom, psi A and psi B orbital, if you calculate the total probability or total electron density, then it comes out to be psi A square plus psi B square. But if they are linearly combined and you get an eigenfunction like psi A plus psi B, then the additional term 2 psi A psi B also crops up, and it is with a positive sign, but it means electron density increases here. Okay. The reverse of this, if you have psi A minus psi B, and if you square this one, psi A minus psi B square, what do you get? You get psi A square plus psi B square minus 2 psi A psi B. So if Cb is equal to minus 1 and you get a psi mo psi A minus psi B, then the electron density decreases by this amount, minus 2 psi A psi B. Okay. This is very important result, because it tells you that two independent hydrogen atoms, if they have and if they do not interact, if they have independent eigenfunctions psi A and psi B, then the total electron density is psi a square plus psi b square. But if they interact, then you have two different functions, two different eigenfunctions. One is psi a plus psi b and another is psi a minus psi b. And if you square this to get the electron density, then psi a plus psi b gives you some additional electron density equal to 2 psi a psi b. And if you have if you square psi a minus psi b, then you get electron density depleted by the same amount minus 2 psi a psi b. So electron density decreases in this case. So one of the energy level corresponds to bonding molecular orbital and another corresponds to anti-bonding molecular orbital. Now obviously, if you have electron density in between the nucleus higher, then it will be an electron bonding it will correspond to bonding molecular orbital, and the corresponding energy is, so I have written the psi a plus psi b, and the corresponding energy is E plus Ha plus Hab divided by Sa plus Sab. And if you have another psi a minus psi b, corresponding energy is E minus and Ha minus Hab and Sa minus Sab is the energy. Okay. So what does it tells you? It tells you that when you linearly combined two hydrogen atom wave function and do the variation treatment, we did not do it variation treatment because we have already done it. We have already done variation treatment and we have got the, and what we do in variation treatment, just a quick recap. In variation treatment, when you guess a wave function, you find out the energy and then you minimize the energy corresponding to minima in order to get the minima of the energy. So, and from there we got the secular determinant. So I have just written directly 2 by 2 determinant. You can do again the practice for your practice the same thing, and you will get the same two linear equations with two coefficients psi a and psi b, and then you can write the linear determinant. Okay. So if we do the linear variation treatment, we get two different energy levels with two different eigenfunctions, psi a plus psi b and psi a minus b. Of course, n is a normalization constant. If you find out the normalization constant, how do we do this? See, the normalization constant is for psi plus and psi minus, I have written n psi a plus psi b and n psi a minus psi b. So the normalization constant will be psi a square d tau is equal to 1. So n square psi a plus psi b square d tau is equal to 1. Okay. And then you can write n square, the psi a plus psi b square d tau means psi a square d tau, psi b square d tau, 2 psi a psi b d tau. So three integrals you have: psi a square d tau, psi b square d tau, 2 psi a psi b d tau. And if you look at these, I talked about earlier also, this is actually a psi a square d tau psi a is orthonormal function of hydrogen atom. This you have to always remember, because we initiated with psi a and psi b. We initiated with psi mo is equal to Ca psi a plus Cb psi b, where psi a and psi b both, Ca psi a plus Cb psi b. So psi a and psi b are the eigenfunctions of the hydrogen atom, which is obviously orthonormal set. Okay. So what does it mean? It is the normalization condition. So this will be equal to 1. So psi b square d tau will also be equal to 1. So 1 plus 1, 2, and then psi a psi b d tau is given a symbol of overlap integral. So 2 Sab is equal to 1. Okay. This you can write as n square 2 into 1 plus Sab is equal to 1. So it is 1 divided by root under 2 into 1 plus Sab is the normalization constant. This we have used psi a plus psi b square. If you use psi a minus psi b square, then you will get a negative sign here, and then you will get a negative sign here, then you will get a negative sign here, and you will get a negative sign here. So this is the normalization constant for the other function, for this function. Okay. For the psi minus or n psi a minus psi b, the normalization constant is 1 divided by root under 2 into within bracket 1 minus Sab. And for the normalization constant for psi plus n psi a plus psi b is 1 divided by root under 2 1 plus Sab. So we have got the normalized eigenfunction for the two molecular orbitals of H2 plus molecule ion, and with the two different energy values. So we can say that the normalized wave functions and corresponding energies are psi plus is 1 over root 2 1 plus SAB, psi A plus psi B. Corresponding energy is E plus HA plus HAB, SA plus SAB. If then psi minus is 1 over root 2 1 minus SAB, psi A minus psi B. Corresponding energy is E minus is HA minus HAB, SA minus SAB. And this diagram tells you that it's a positive combination, it's a negative combination of the two hydrogen atom wave functions, psi A psi B and psi A psi B. When they combine, if it's a negative combination, so this becomes a negative sign. And you see, this is the electron density decrease. You see here, in this case, the electron density is, I think the plot should be more like this one. Okay. Should be like this one that you can draw. Okay. So electron density is higher here, but in between the nucleus, if you find, if this is your A nucleus, this is your B nucleus, then in between the nucleus there is no electron density. Very negligible electron density. Now here you see it's a huge rise in the electron density. Okay, and as compared to this stage where it is being formed, the electron density further decreases here when the molecular orbital is formed. So we say this to be anti-bonding molecular orbital and this to be bonding molecular orbital, and then what you draw in your from your +2 level textbook, this is what you draw is the molecular orbital diagram. That if you have psi 1sa, psi 1sb, and when they combine, they give you this particular energy levels. Okay, and you say sigma 1sa, sigma 1sb, and since you have only one electron, so one electron is filled here. So we got from the linear addition treatment two different energy levels for the H2 plus molecule ion. Okay, and we also got the normalized eigenfunction for both these energy levels. What we can do is that we can find out that what should be the energy gap between these two. Okay, what should be the energy gap between these two molecular orbitals, means bonding molecular orbitals and anti-bonding molecular orbitals. Okay. Another thing what we can do is that whatever energy we have written here is in forms of HAA, HAB, SAA, SAB. What does it mean? How can we find out the value of the energy? The value of the energy should be in the unit of the energy, and HAA, HAB, SAA, SAB are the integrals. Okay. So this we will see that how do we actually find the energy and what that energy tells you and what is the energy gap between these two energy levels in the next module. We will talk about this. Okay, thank you.